Good morning, students. In this class, we are going to discuss about the time domain analysis or time response analysis of the control system. So earlier in the previous chapter, we have discussed about the control system in frequency domain analysis. But in this chapter, we are going to discuss about the time domain or time response analysis. That means we are calculating the response of the system with respect to time. Time response analysis means whatever the signals we are going to consider in time response and varies with respect to time. So that means time response analysis are varies with respect to time. For example, the input signal or the reference signal, the input signal or reference signal is R of t and C of t is the controlled output and it can be vary with respect to time. In time domain analysis, the response of the dynamic system is to change an input is expressed as a function of time. It is possible to compute the time response of a system if the nature of the input and the mathematical model of the system are known. What is meant by the time response analysis means, you know the response is the output of the system. So time response analysis is nothing but the variation of the output of the system with respect to time is called time response analysis. With this time response analysis, we can study the stability of the system, accuracy of the system. And up to now, we are discussing about the output transforms. That means we can consider the frequency domain of the outputs. But here in time response analysis, we are going to calculate the outputs with respect to time. Usually the input signals to control systems are known as fully ahead of the time. And it is therefore difficult to express the actual input signals mathematically by simple equations. Before we are discussing about the time response analysis, generally the control systems are depending upon the linearity at two times. One is linear control systems, second one is non-linear control systems. So in such systems, which is the principles of the system is superposition, proportionality is obeyed. That system is called linear control system. Non-linear systems do not obey the law of the superposition. The stability of the non-linear systems depends on root location as well as the initial conditions and type of the inputs. Non-linear systems exhibit self-sustained oscillations of frequency, that is fixed frequency. Similarly, the classification of control systems that is by varying the time, that control systems are two types. One is time varying control system. Second one is time invariant control system. Systems whose parameters vary with respect to time are called time varying control systems. When parameters do not vary with respect to time are called time invariant control system. For example, the mass of the missile or rocket reduces as a fuel is burnt and hence the parameter mass is a time varying. So with that mass is a varying, that is reducing or increasing by varying with respect to time. And this control system is a example for the time varying type control system. So for example, you see here the time response. The time response of a system is the output or response which is a function of the time when the input excitation is applied. Time response of a control system consisting of two parts. One is transient response, second one is steady state response. Here I am going to consider a control system. For example, I am taking the simple, the basic negative feedback system. So what is the transfer function? Transfer function already we have determined in earlier classes in frequency domain concept. T of S is equal to C of S by R of S, the value is equal to G by 1 plus GH. Here what is G? G is the open loop gain and H is the closed loop path gain. That is G of S by 1 plus G of S into H of S. For example, with that, we are calculating the response with respect to time. How to determine it? C of S by R of S. If you transfer that, if you move the R of S in that direction, then C of S is equal to R of S into G of S by 1 plus G of S into H of S. Then how to calculate the C of t? What is C of t? The output with respect to time. So what is C of S? The output with respect to frequency response. That is C of S. So from C of S, how to calculate the C of t? by using the inverse Laplace transform. So if you apply the inverse Laplace transform of the negative feedback system, then C of t is equal to Laplace inverse of R of s into G of s by 1 plus G of s into H of s. Likewise, we are calculating the time response of the any system. We are going, that is, with respect to the, we are having the two types of the responses. One is transient response, the second one is steady state response. If it is expressed mathematically, the two responses, C of t is equal to Ct of t is a transient response and CSS of t is a steady state. Here represent SS means steady state response. C1 of t is a transient response. CSS of t is a steady state response. What is transient response? Transient response is nothing but the response of the system which varies with respect to time. Transient, the name itself is give the clarity. Transient response means the response is changes with respect to time. But whereas in a steady state response, in a steady state response, it won't, the output of the system won't change with respect to the time. It will come continuously in a system. So that is called the steady state response. So the transient response is a part of the response which goes to zero as increases. Mathematically, it represented as limit t tends to infinity, C1 of t is equal to 0. The transient response may be exponential or oscillatory in nature. Steady state, the steady state response is the part of the total response after the transient has died. Steady state error. If the steady state response of the output does not match with the input, then the system has steady state error and it is denoted by small e suffix ss. Time response of the dynamic system, the response to an input expressed as a function of time. For example, let us assume that this is a time response analysis. The time response analysis, has already I am saying that it has two components. One is transient response and steady state response. What is the meaning of transient response? The response is changes with respect to time. And what is steady state response? It won't change with respect to time. So this is the time we clearly see that when the response of the system is changed from the equilibrium and it takes some time to settle down. So it will take some time. So this is a response. It will take some time to settle down. Once it is settled down, it is a steady state response. The response of the system after the transient response is called steady state. Once it is settled down, then it won't change with respect to time. It is constant. So that is called steady state response. So that is the response of the system after the transient response is called the steady state response. Clearly see from the diagram, with the same diagram. So this variation with respect to time, see that it is a transient response, and where it is stable, it will be settled down. It won't change with respect to time. That is called steady state response. Transient response depending upon the system poles and not only the type of the inputs. It is therefore sufficient to analyze the transient response using a step inputs. The steady state response depending upon the system dynamics and the input quantity. It is then examined using the different test signals by final value theorem. Standard test signals. So already we have the standard test signals are there. So we are going to study about the transient analysis. You need to know about the test signals. In this topic, generally we are in this topic in the topic of the signals and systems also, we are discussing about the generally impulse signal and ramp signal. But here we are going to discuss about some other extra signals like ramp signal and parabolic signals are considered as a test signals. So the characteristics, that is very important point. The characteristics of the actual input signals are sudden change, sudden shock, constant velocity, and constant acceleration. This is very important. The characteristics of the actual test signal input signals are sudden shock, sudden change, constant velocity, and constant acceleration. The dynamic behavior of the system is therefore judged and compared under the application of the standard test signals like an impulse signal, a step signal, a constant velocity, and a constant acceleration. The other standard signals of the great importance is a sinusoidal signal. We consider one by one the standard test signals. First one is impulse test signals. So what is impulse signal, test signal? It is represented by del of t, that is with respect to time, delta, the del of t. Del of t is equal to a. What is a? Amplitude. That is equal to a if t is equal to 0. You see here, if t is equal to 0, then it is, if t is equal to 0, that is equal to amplitude. If it is 0, the value is 0 if it is not equal to 0, whether it is t is greater than 0 or less than 0. If t is less than 0 or greater than 0, then the delta of t is equal to 0 only. Only the value of the impulse is represented when the t is equal to 0. When it gives the unit impulse, when amplitude a is equal to 1. If a is equal to 1, the impulse signal is called the unit impulse signal. Similarly, second one is step signal. So the step signal imitates the sudden change characteristic of actual input signal. It is represented by u of t. U of t is equal to a. So the ramp signal is equal to amplitude when t is greater than or equal to 0. Even when the t is equal to 0 and it starts from t is equal to 0. Right? If when it starts from t is equal to 0, if t is greater than or equal to 0, it shows that value is equal to a. When t is less than 0, that means the less than 0 values, that the step signal is 0. When t is greater than or equal to 0, the impulse signal is, the step signal is equal to amplitude. When amplitude a is equal to 1, the step signal is called as unit step signal, and it is represented like this. Third one is ramp signal. The ramp signal is imitate the constant velocity characteristic of actual input signal. That is, it is represented by small r of t. R of t is equal to a, capital A into t. When t is greater than or equal to 0, you clearly see that it starts from 0 only. When t is equal to 0 or greater than 0, the value r of t is equal to a into t. And the value is equal to 0 when t is less than 0. You see clearly in the left side, when t is less than 0, there is no ramp signal. Right. So when it is called as a unit ramp, when a is equal to 1, the ramp signal is called as unit ramp signal. And it will show the ramp signal with a slope a in different concepts. With a slope a, it is represented like this. Unit ramp signal is represented like this. So this is the actual ramp signal. This is a unit ramp signal. Last one is parabolic signal. So the parabolic signal imitates the constant acceleration characteristic of actual input signal p of t. It is represented by x of t or p of t. That value is equal to a into t square by 2. When t is greater than or equal to 0. And the value is equal to 0 when t is less than 0. So as per this diagram, it can be shown like that. The curve is like the parabola. So that's why it's a parabolic signal. So the value is only mentioned when t is greater than or equal to 0. It starts from 0 only. When t is less than 0, the value is 0. When t is less than 0, the value is 0. When t is greater than or equal to 0, the value is equal to at square by 2. When it is called the unit parabolic signal, when amplitude a is equal to 1, the parabolic signal is called unit parabolic signal. The parabolic signal with slope difference also mentioned like this, and unit parabolic signal is mentioned like this. So the relation between the standard test signals. So how to calculate the relation of, for example, del of t. So you clearly see that del of t is equal to a when t is equal to 0, and it is equal to 0 when t is not equal to 0. Step signal u of t is equal to a when t is greater than or equal to 0, and the value is equal to 0 when t is less than 0. Similarly, ramp signal r of t is equal to a into t when t is greater than or equal to 0, and this value is equal to 0 when t is less than 0. And the parabolic signal x of t or p of t is equal to at square by 2 when t is greater than or equal to 0, and the value is equal to 0 when t is less than 0. The relation between the standard text signals. For example, if one is known, the second one we have to calculate. We have to get the relation between all the standard test signals. So del of t. So that is, what is the meaning of this? The meaning of this is integral of, you see here, integral of del of t is equal to u of t. The integral of u of t is equal to r of t. Integral of r of t is equal to p of t. Integral of impulse signal is equal to step signal. Integral of step signal is equal to ramp signal. Integral of ramp signal is equal to parabolic signal. Similarly, in the reverse side, like this. That means the differentiation of parabolic signal is the ramp signal. The differentiation of ramp signal is the step signal, and the differentiation of the step signal is the input signal. For example, if you know the input signal, if you know the that is u of t, then how to calculate the del of t from in terms of, for example, if you want to calculate the del of t, this value in terms of r of t. So you want to calculate del of t in terms of r of t. How to represent r of t? So del of t is equal to, you see from this concept, del of t is equal to d by dt times of u of t. Del of t is equal to d by dt times of u of t. And what is u of t? D by dt times of r of t. Therefore, del of t in terms of r of t is d square by dt square into r of t. So that's why with these relations, we can calculate any test signal from any test signal. So that's why this relation is very important. So in this class, we have discussed about the time response concepts. And in the next class, we are going to discuss about the order of the system and the Laplace transforms of the test signals. Okay, thank you.